Okay. I'm Yizhou Zhang from Cornell University, and this is joint work with Guido Salvanaski, Quinn Bechtel, Barbara Liskov, and Andrew Myers. Whether exceptions should be statically checked or not is perhaps the single most debated issue about the design of the Java programming language. Uncalled exceptions crash programs, so a static checking should in principle make software more reliable. However, opponents of static checking argue that checked exceptions are too rigid to support the common ways that software is built. In particular, they do not support higher-order programming well. To see the problem, consider this higher-order function map written in Java. It takes a list of t's and a function that transforms a t to an r, and it returns a list of r's. Parsefile is a method that declares the checked I/O exception, and the programming task here is to parse a list of files. So the programmer calls map and passes parsefile to it as a lambda expression. Because parsefile declares I/O exception, the programmer then writes a handler for it to account for this unusual condition. So this code looks like what we want, but it does not type check in Java. The Java compiler reports two errors for it. So first, there is an exception mismatch between parsefile and the function interface, which is the interface of lambda expressions. And the second, the Java compiler thinks that no method call made in the try block is statically known to give rise to I/O exceptions, so stuff in the catch block would be unreachable. To address this problem, Java 8 introduces an unchecked exception type called unchecked I/O exception. And the programmer is supposed to use it in the following way. In the lambda expression, the programmer wraps an I/O exception into an unchecked I/O exception. And in the calling code, the programmer does the unwrapping. Not only is this code verbose, it also abandons static checking, which defeats the purpose of having checked exceptions in the first place. The unpleasant experience with Java's checked exceptions is off-putting. To quote Anders Hallsberg, the principal designer of C#, more thinking is needed before we put some kind of checked exceptions mechanism in place. But 2 decades of thinking does not turn out to be fruitful, as almost every programming language designed after Java has chosen not to include statically checked exceptions. Unchecked exceptions can provide the missing flexibility, but they are hard to tame. Not only do they contribute to uncalled exceptions, they also contribute to exceptions that are accidentally caught. Consider this implementation of map. It uses an iterator to walk through the list and applies the transformation f to each element in the list. The method next here, defined by interface iterator, declares no such element exception. This exception indicates that the iterator can produce no more element. So we put the method call in a try catch. The catch block here is intended for the method call to next. But we also notice that the formal parameter f could be passed a function that declares the same exception type, no such element exception. And when this exception does happen at the runtime by applying f, it will be caught by the catch block, but the catch block is not intended for it. After this exception is mistakenly handled by the catch block, the higher order function map will return normally, but the returned list is only the transformation of a prefix of the input list, and the caller of map is not informed about this problem. So we have a silent bug here. Both uncalled exceptions and accidentally called exceptions harm software reliability, so Java makes certain exception types checked. But the problems remain with unchecked exception types, and the checked exception types are too rigid to work with. We believe that Java asks the wrong question. The distinction of checked versus unchecked should not be a property of the exception type, but should rather be dependent on the context that the exception is propagating through. In a context that is aware of the exception, like the caller of map, the exception should be checked. And in a context that is oblivious to exception, like the definition of map, the exception should be effectively unchecked and tunnel through the intermediate exception oblivious context. This insight allows our design to offer the strong guarantee that intentional exceptions are always caught, but never accidentally caught. We explore this design in the context of the genus programming language. Genus is a variant of Java with an expressive generics mechanism. It inherits from Java the language constructs for exception handling, but as we'll see in this work, we change their semantics. Although this work is based off of genus, the core ideas should be applicable to other programming languages, including C#, Scala, and even ML. Designing an exception mechanism requires understanding the design goes well. In practice, there are two quite different classes of exceptional events. The first class is to use exceptions to indicate software failure, where the programmer's assumptions about software or the environment are violated. This typically means programmer mistakes. The second class is to use exceptions to indicate an unusual but planned for state of program execution. This could be a potential I/O problem that the programmer is conscious of, or it could just be an unusual case of an algorithm. For failures, the programmer needs the ability to debug the stopped program to discover why the failure occurred, so a stack trace would be helpful in this case. For unusual conditions, since they are unusual, it is important to have static checking that checks the programmer does not forget to handle them. And since they are planned for, throwing and catching exception should be fast. The focus of this talk will be about unusual conditions, but as a warm-up, let's first take a quick look at the failure events. Suppose the programmer writes a method called first that fetches the first element from an iterable. The programmer does this by invoking the method next on the iterator. The method next here declares no such element exception, but this exception should never happen in our case because the precondition of first is that the iterator is non-empty. In genus, the programmer can attach a fails clause to the method header to indicate that such an exception is impossible under their assumption. But suppose the programmer does make a mistake and passes an empty iterable to first. Then after the no such element exception is propagated to the stack frame of first, it will be converted into a failure and crash this program. This failure exception will also gather a stack trace to help the programmer debug their program. So this is how we handle failures. For the other class of exceptional events, we want to enforce static checking even in the face of higher order functions. Recall that this code does not type check in Java, but if we rewrite it into genus, it ordinarily type checks. We still have this exception mismatch, but that's okay. To account for this mismatch, we notice that the higher order function map is oblivious to whatever exceptions raised by f, because the type function does not declare any exceptions. And because map is exception oblivious, it cannot be expected to handle the extra I/O exception. By contrast, the calling code here is aware of the extra exception because it passes parse file to map. Therefore, the calling code should be responsible for handling the extra I/O exception. At runtime, an I/O exception raised by calling parse file will tunnel through the intermediate exception oblivious context and arrive at the context aware of it and be caught there. Alternatively, this exception could be rethrown to the caller of the caller map, or be converted to a failure, or be tunneled again if the caller map was itself passed as an argument to some exception oblivious code. No matter what happens, exception handling is statically enforced, and the throwing and catching exception is efficient because it does not incur the outrageous cost of gathering a stack trace. As I showed earlier, the subtle problem of accidentally catching exceptions could arise when higher order functions themselves use exceptions. For example, recall that this higher order function could result in an accidentally caught no such element exception. We call this problem exception capture by analogy with the problem of variable capture in dynamically scoped languages. Variable capture arises because variable identifiers collide in an unexpected way. Analogously, exception capture arises because exception identifiers collide in an unexpected way. And here, an exception identifier is solely the exception type. So for instance, the two exceptions raised by applying f and the calling next are both identified by their types, which could both be the same no such element exception type, so a collision is possible. By contrast, in genus, the way that exceptions propagate is context-dependent. This means that exception identifiers include a notion of context, and this makes exception capture impossible. For example, we know that our map code is oblivious to exceptions raised by f. But what this really means is that an exception raised by f will have a different context than the current one. The current context cannot handle any exceptions raised by f, simply because the exception identifiers differ. This notion of context awareness perhaps sounds rather vague at this point. It is made concrete by blame labels. This idea of blame labels is borrowed from work on gradual typing. In gradual typing, a type mismatch results in a typecast being inserted and a blame label being assigned to that particular typecast. So if a cast failure does happen at the runtime, it can be attributed to the appropriate context represented by a blame label. In genus, an exception mismatch results in a blame label being assigned, so that an exception at the runtime can be propagated to the appropriate context represented by the exception's blame label. The key difference here is that gradual typing uses blame labels for runtime enforcement, while genus uses them for compile time enforcement. In genus, blame labels impose a static responsibility on the context to handle the corresponding exceptions. And because this is a static enforcement, uncalled exceptions are made impossible. And because the context is only allowed to handle the corresponding exceptions, accidentally called exceptions are made impossible. Returning to our map example, the calling code here passes the method next of iterator to map. Because next declares no such element exception, we have an exception mismatch, and a blame label L1 is assigned for this mismatch. The context is then required to handle this extra exception. In this case, the context handles it by converting it to a failure. Our map code makes a method call to next. This context expects this method call to return value, but this method call could instead raise an exception. So we also have a mismatch in this case, and a blame label L2 is assigned for it. The context then handles this exception by catching it. A no such element exception raised by applying f will have blame label L1, so it will be tunneled to the context represented by L1. Design patterns like iterator, visitor, and factory are essentially higher order, so particular implementations of these abstractions may also want to throw new exceptions. For example, we can have various subtypes of iterator that adds various types of exceptions. And in fact, these examples are all drawn from real code bases. Unfortunately, they violate the requirement of behavioral subtyping, which has been interpreted to require that subtypes should not add new exceptions. We address this need for flexibility by giving a new interpretation to behavioral subtyping. Subtypes are allowed to add new exceptions if their supertype is weak. For example, factory is a weak interface, so it's okay to define a subtype, connection factory, that serves as a factory for SQL connections, but also adds the extra SQL exception. However, using a connection factory as a factory for SQL connections results in a blame label being assigned. And this blame label imposes a responsibility on the context to handle the extra SQL exception. So in other words, our mechanism weakens the requirement of behavioral subtyping, but does not weaken static checking. Under the hood, this type checking works by a local constraint-based program analysis. It connects blame labels to exception mismatches, that is, sets of extra exceptions that methods can throw. And this analysis allows us to track the exception mismatches inherent in weakly typed local variables. Since blame labels are statically scoped, it is important to make sure that their corresponding exception mismatches do not escape their scopes. Otherwise, the exceptions would not be guaranteed to be handled. Consider this object pool class. It uses a factory to support object pooling. Its borrow method makes a method call on the instance variable factory to create a new object if there is no idle object in the pool. Suppose we were allowed to create a new object pool for SQL connections using connection factory, then the extra SQL exception could be raised when the method call to borrow were made. But this method call could be delayed until outside of the context that is aware of the current exception mismatch. And at that point, the context would already be exception oblivious, so the extra SQL exception would not be guaranteed to be handled. So this motivates an escape analysis, and it turns out that this analysis can be encoded in the same constraint-based mismatch analysis. For example, this analysis produces an unsatisfiable constraint for the assignment to the escape instance variable factory, so the genus compiler reports a warning for it. Beyond escape analysis, genus provides annotations for the programmers to express things like object pool in a type-safe manner. The Java-style annotation exec can be used to indicate that exception mismatch is not allowed. But this allowing exception mismatch would be too restrictive in this case. In fact, a genus programmer can use constraint generics to indicate that exception mismatch is polymorphic with respect to the constraint. To do this, we define factory as a constraint. A constraint in genus is like a type class in Haskell. We can then put a where clause constraint in the class header of object pool to require its type parameter t to provide a make operation. Constraints are satisfied by models. This model connection factory is a factory for SQL connections and therefore adds SQL exception. A model in genus is like a type class instance in Haskell, but unlike a Haskell instance, models become part of the instantiated generic types. The client code here creates and uses an object pool. The model being used here is connection factory. It's inferred by the compiler because there is no ambiguity in this context about which factory to use for SQL connections. And because the model being used is part of the instantiated generic type, the extra SQL exception can be tracked precisely. We can also compare this genus code with what would happen in Java. In fact, this is what happens in Java. It's code extracted from the Apache Commons project. The factory interface declares throws exception, so a particular implementation can refine this exception. But this also forces the client code to handle the overly general exception type. And this is no better and perhaps worse than using a runtime exception. And catching the overly general exception type can raise the risk of exception capture. We have formalized the core aspects of this new exception mechanism and also proved the soundness theorem that well-typed programs handle their exceptions. We've also built a compiler for it by extending the base genus compiler. Our code generation currently works by translating genus code into Java. To avoid exception capture, blame labels must be reified so that exception identifiers, so that exceptions can acquire new identities in the generated Java code. But this inevitably introduces a cost to the normal control flow paths in the genus to Java translation. So the challenge here is to make this cost negligible. To evaluate our design, we ported the Java collections framework into genus. Our static checking found unreachable catch blocks in this most widely used Java library, and our new semantics of exceptions prevents previously reported exception capture bugs. We also ported various exception tunneling code into genus, and the resulting genus code is both safer and cleaner. We managed to remove 200 out of 1,000 lines of code in the Java C visitor class by removing the need to use unchecked exception wrappers. Our performance evaluation tried to answer two questions. Our implementation reifies blame labels to avoid exception capture. So the first question to ask here is, does reifying blame labels incur slow down normal case code that does not make heavy use of exceptions? The second question is, what speed up can be achieved by not gathering a stack trace on exception heavy code by not gathering a stack trace? To answer the first question, we ported the Yizhou benchmark suite and the Sunflow program from the Kavo benchmark suite as benchmarks for normal case code. In this graph here shows the relative running time of the new genus language compared to the genus before extension. The genus before extension is a good baseline because it uses exactly Java's exception mechanism, and lower is better in this graph. Despite the small cost introduced to reify blame labels, we saw a 2.4% speed up across the benchmarks we used. And in the worst case among these benchmarks, the slowdown is less than 0.5%. So it's fair to say that our current implementation does not impose a discernible slowdown on normal case code. To answer the second question, we ported a text parsing package. This code base makes heavy use of exceptions for backtracking. And as we expected, the benefit of not gathering a stack trace is conspicuous. Since our implementation targets Java, it's not surprising that similar performance can be achieved with Java. But this requires writing Java code in a non-standard way to turn off stack trace collection and to cache exception objects. Using program analysis to infer exceptional control flow has been a popular research topic. However, these analyses necessarily entail a trade-off between performance and precision, and they require global reasoning that does not aid programmers in reasoning about code. Some recent language extensions or language designs have attempted to address the rigidity of checked exceptions through an approach called exception polymorphism. This approach parameterizes higher-order code with the exceptions of their arguments. So it necessarily imposes a notational burden on higher-order functions. But more fundamentally, this approach does not address the subtle problem of exception capture. We feel that exceptions in today's languages are being trapped in two vicious cycles. The unsatisfactory semantics and the slow implementations of exceptions push programmers away from using exceptions. And this ineffective and infrequent use of exceptions, in turn, pushes language designers and language implementers away from designing and optimizing for exceptions. We hope our work breaks the vicious cycles. Our design combines the benefits of static checking and the flexibility of unchecked exceptions, and also offers good performance. We hope our design will offer guidance to language designers on making exceptions more principled and more appealing to programmers, and also offer an incentive to language implementers to make exceptions more efficient. Thank you.
If I love this mechanism and I wanted to add it to a functional programming language like maybe OCaml or Haskell, what difficulties would I run into, do you think, in doing that?
I don't think there is a significant difficulty in adding to languages in the ML family. But for Haskell, since it's a lazy language, and there's a tricky interaction between exceptions and this laziness. So I think Simon Peyton Giles wrote a paper in the 90s about how to handle this in Haskell.
So your benchmarks were like within, the original running time, pretty close, except for one of the programs looked like it had a significant speed up. Why is that?
Yeah, thanks for asking that question. So the speed up here almost exclusively comes from this health benchmark over there. And what happens here is that genus desugars for each loops in a different way than Java does. So you can see that Java desugars for each loops by calling hasNext on each loop iteration, but the genus desugars for each loops by only throwing and catching exception at the end of the loop. And this can have a perceptible impact on your performance if the loop body is iterated for a great number of times.
So you showed how to avoid this exception capture problem for high order functions, but what if I want to capture some of the exceptions? Say my high order function is going to know that my underlying function uses exceptions for control flow in an interesting way, and I want to handle some of those. How would that work in your system?
So for modularity and for modular reasoning, I think it is better not to catch those exceptions in your higher order functions. But if you do want to catch those, so for instance, it's quite reasonable to catch exceptions at the top level of your program or at the boundary between software components, then genus supports this catch-all construct that it catches exceptions regardless of whether they are failure or not.
So one example I can think of would be, say, parser combinators, where exceptions are representing failures that are common, like in the parsing example you gave, but there I would just have to catch at the top level.
Yeah.